Episode 9 Snowball Earth, the first freeze. I want you to do something today. I want you to imagine a world of ice. Not just the ice at the poles, but as we have today, but ice everywhere. An ice covering the ocean from equator to pole. Ice sheets kilometers thick grinding over the continents. Ice reflecting so much sunlight that the planet appears as a brilliant white ball from the space, frozen and seemingly lifeless. This sounds like science fiction, a vision of a distant planet orbiting a dying star, but it may have been Earth's reality, not once, but multiple times in our planet's history. These episodes, called Snowball Earth events, represent some of the most extreme climate changes Earth has ever experienced. The first of these deep freeze events occurred around 2.4 to 2.2 billion years ago, in the aftermath of the Great Oxidation events. It is called the Huronian glaciation, and it may have been triggered by the very same rise in oxygen that we discussed in the last episode. This is the story of that first great freeze, of how Earth became a snowball, of how life survived beneath the ice, and of how the planet eventually thawed, emerging from the deep freeze to continue its evolutionary journey. And to understand how Earth could freeze so completely, we need to understand climate feedbacks, the way in which changes in one part of the climate system can amplify the changes in another parts. This, the most important feedback for understanding Snowball Earth, is the ice albedo feedback. Albedo is a measure of reflectivity, of how much sunlight the surface reflects rather than absorbs. Fresh snow has a high albedo, reflecting up to 90% of incoming sunlight. Dark ocean has a low albedo, absorbing most of the sunlight that hits it. Here is how the feedback works. Suppose Earth begins to cool for some reason. Maybe volcanic activity decreases, reducing the amount of carbon dioxide in the atmosphere and weakening the greenhouse effect. Or maybe the continents drift into positions that allow ocean currents to circulate more efficiently, transporting heat to the poles and cooling the equator. Whatever the cause, as the Earth cools, ice begins to form at higher latitudes near the poles. This ice has the high albedo, reflecting more sunlight back to space than the dark water or land it covers. This means less solar energy is absorbed by the planet, which causes it to cool further. The cooling causes more ice to form, which increases the albedo further, which causes more cooling. This is a positive feedback loop, a runaway process. Once it starts, it accelerates, with each step reinforcing the next. If the ice advances far enough, if it spreads from the poles to becomes so reflective that it cannot absorb enough solar energy to maintain liquid water anywhere. The entire planet freezes, locked in ice from pole to pole. This is Snowball Earth. But wait, if Earth freezes completely, how does it ever thaw? If the ice reflects all the sunlight, how does the planet warm up again? This is the Snowball Earth paradox, and it puzzled scientists for years. The answer lies in volcanism. Even during Snowball Earth, volcanic activity continues. Volcanoes are powered by the heat from the Earth's interior, not from the sun, so they keep erupting even when the surface is frozen. And when they erupt, they release carbon dioxide into the atmosphere. Normally, this carbon dioxide would have been removed from the atmosphere by weathering, the process we discussed in the earlier episodes where carbon dioxide dissolves in the rainwater, forms carbonic acid, reacts with rocks, and is eventually locked away in carbonate minerals. But during a Snowball Earth event, weathering stops or at least slows dramatically. The land is covered in ice. There is no water, there is no rain, or very little. The carbon dioxide released by the volcanoes has nowhere to go. It accumulates in the atmosphere. Over millions of years, the carbon dioxide concentration builds up 10 times pre-industrial levels, 100 times, perhaps even 1,000 times. The greenhouse effect becomes incredibly strong, far stronger than anything Earth has ever experienced in recent geological history. And eventually, perhaps after 10 million years, wow, the greenhouse effect becomes strong enough to overcome the isobeta feedback. The planet begins to warm. The ice at the equator, the thinnest and most vulnerable, begins to melt. Dark ocean water is exposed, absorbing more sunlight. The warming accelerates. The isobeta feedback, which drove the freezing, now runs in reverse, driving the thawing. The planet transitions rapidly from a frozen snowball to a hothouse, with the temperatures soaring as the thick carbon dioxide atmosphere traps heat. This is the Snowball Earth cycle, freeze driven by the isobeta feedback, accumulation of carbon dioxide, thaw driven by the greenhouse effect, and in the aftermath, a world transformed. The Huronian glaciation, the first Snowball Earth event for which we have good evidence, occurred between about 2.4 and 2.2 billion years ago in 3 distinct pulses. This means Earth may have frozen and thawed 3 separate times over a period of 200 million years. Wow, that's interesting. The evidence for this glaciation comes from rocks deposited during this period, found on several continents. These rocks include dropstones, pebbles, and boulders that were carried by glacial ice and dropped into marine sediments when the ice melted. They include stalactites, deposits of unsorted rocks, and sediment characteristics of glacial erosion. And most tellingly, they include these glacial deposits at locations they were near the equator at the time based on paleomagnetic measurements. Glacial ice at the equator can only mean one thing: the planet was frozen from pole to pole, or very nearly so. This is the signature of Snowball Earth. But was the planet truly completely frozen, with ice covering even the equatorial oceans? Or was it more of a slush bowl with ice covering most of the planet, but with some areas of open water near the equator kept liquid by the heat of the sun? This question is still debated. Some models suggest that the complete freezing is possible and perhaps even likely, given the strength of the ice albedo feedback. Others suggest that there would always be some areas of open water, at least in the tropics where the sun's heat is strongest. The difference matters for life. If the ocean surface was completely removed, photosynthesis would have been impossible in the ocean. No light could penetrate the ice, and photosynthetic organisms would have died or gone dormant. But if there were some areas of open water, or if the ice was thin enough to allow some light through, photosynthesis could have continued, or the photosynthesis could have continued, at least in refuge. Deep in the ocean, below the ice, life almost certainly persisted. Chemosynthetic organisms, bacteria, and archaea that derive energy from chemical reactions rather than from sunlight would have been unaffected by the freezing of the surface. Hydrothermal vents would have continued to operate, providing energy and nutrients. The deep ocean biosphere, insulated from the frozen surface, would have carried on. But what about the photosynthetic organisms, the cyanobacteria that had so recently transformed the planet by producing oxygen? How did they survive? One possibility is that they survived in patches of open water, if such existed, or under thin ice through which some light could penetrate. Another possibility is that they went dormant, forming spores or other resistance structures that could survive for millions of years without light, waiting for the ice to melt. Modern cyanobacteria are capable of remarkable feats of survival. Some can form spores that remain viable for years or even decades in harsh conditions. Perhaps ancient cyanobacteria had similar abilities, allowing them to survive the long Snowball Earth freeze. A third possibility is that photosynthetic organisms survived in refuges on lands, in geothermal areas where volcanic heat kept patches of ground ice-free, or in meltwater pools on the surface of glaciers. These environments would have been harsh and limited, but they might have been enough to allow some lineages to persist. do not know for certain how life survived the Huronian glaciation. The rock record from this time is limited, and fossils are rare, but we know that the life did survive because it was present before the glaciation and present after. Somehow, despite the extreme cold and the near total freezing of the planet, life persisted. And when the ice finally melted, when the carbon dioxide accumulated by millions of years of volcanic activity finally warmed the planet enough to end the freeze, life rebounded. The ocean newly thawed and enriched with nutrients released from the glacial erosion would have been a fertile environment. Photosynthetic organisms spread across the surface. Evolution resumed. The aftermath of the Snowball Earth event would have been a strange and violent time. The planet having swung from extreme cold to extreme heat would have experienced intense weathering. The thick carbon dioxide atmosphere would have created intense rainfall, perhaps more intense than Earth has seen in any other time of its history. This rain, heavy with dissolved carbon dioxide, would have been highly acidic, rapidly weathering the rocks exposed by glacial erosion. Within a few 100,000 years, much of the carbon dioxide that had accumulated during the freeze would have been removed from the atmosphere, locked away in carbonate minerals deposited on the seafloor. These carbonate minerals, laid down in the immediate aftermath of Snowball Earth events, are called cap carbonates, and they are one of the distinctive signatures of these events. They appear in the rock records as layers of limestone or dolomite directly overlying the glacial deposits, a sharp transition from ice age to hothouse preserved in stone. The Huronian glaciation and the Snowball Earth events that would come later were not just catastrophes for life, they were also opportunities. The glaciation would have caused extinctions, wiping out species that could not adapt to these extreme conditions, but it also would have created new ecological niches, new opportunities for evolution. The freeze-thaw cycle would have physically ground up rocks, creating new mineral surfaces and releasing nutrients into the ocean. This would have fueled biological productivity in the aftermath, allowing life to flourish in the nutrient-rich post-glacial ocean, and the extreme conditions would have created strong selective pressures favoring organisms that could survive cold, darkness, and variable conditions. These survivors would have been the ancestors of new lineages adapted to changing planets. The Huronian glaciation also had lasting effects on Earth's climate system. The rise of oxygen that helped trigger the glaciation was permanent, at least in the sense that oxygen levels would never again drop to zero. The Earth had crossed the threshold from a reducing planet to an oxidizing one, and there was no going back. The glaciation itself may have affected the evolution of plate tectonics and the formation of continents. The weight of the ice sheet, kilometers thick, would have pressed down on the crust, affecting mantle convection. The erosion caused by glaciers would have moved vast amounts of rock and sediment, reshaping its surface, and the climate feedbacks revealed by the glaciation, the isobeam feedback, and the carbon dioxide greenhouse effect would remain important throughout Earth's subsequent history. These feedbacks, the tendency of ice to beget more ice, and the tendency of volcanic carbon dioxide to accumulate during ice ages, and drive warming would shape every subsequent ice age and every deglaciation. As we close this episode, let us reflect on the resilience of Earth and of life. A planet-wide freeze lasting millions of years seems like it should be the end of the story. How could anything survive such extreme conditions? And yet, life did survive. It persisted in refuges, in the deep ocean, perhaps in meltwater pools or in thin patches of open water, and when conditions improved, it rebounded, spreading and diversifying, resuming the evolutionary journey. This resilience is built into the nature of life. Evolution creates diversity, and diversity creates resilience. With millions of species, each adapted to different conditions, it is nearly impossible to create an environment so harsh that nothing can survive. Some organisms will always find a way. In the hottest vents, there are bacteria. In the coldest ice, there are bacteria. In the driest deserts, in the most acidic pools, the deepest rocks, there is life. And during Snowball Earth, despite the freeze, life persisted. The Huronian glaciation was the first great freeze, but it would not be the last. Earth would experience at least 2 more snowball or near snowball events around 750 to 650 million years ago during the Cryogenian period. We will discuss those events in future episodes. But even with these multiple freeze events, even with the catastrophic climate swings they represent, life not only survived but evolved, becoming more complex, more diverse, more adaptable with each passing eon. In the next episode, we will turn to different subject, the boring billion, a period of Earth's history from about 1.8 to 800 million, 1.8 billion to 800 million years ago, when not much seemed to be happening. The climate was stable, evolution appeared slow, and Earth seemed to be in a holding pattern. But appearances can be deceiving. Beneath the surface, in an invisible world of cellular evolution, crucial changes were occurring. Changes that would set the stage for the explosion of complex life that was to come. The boring billion wasn't boring at all. It was time of preparation, a slow build-up to revolution. The freeze is over, the ice has melted, the ocean teems with life once more. But the story is far from over. Earth has billions of years ahead, countless transformations yet to undergo. The journey continues through ice and fire, through catastrophe and renewal, towards a future we